So in this video, we will show the set difference law, which is represented like this, is the union of A minus B, union B minus A. Okay, we need to prove it. We will just go from left hand side to right hand side. We don't have to prove the other way around. For now, we'll just make it simple. Okay, so we are going to use the set identity laws and use the set builder notation, right? So let's X belongs to a set difference B, right? So what does it mean? It means several things, right? If you, for those people who are refresh your mind, the class we did this, right? So if you have and the set difference law basically states what is the X belongs to either that or that, right? So that could be written as is, I go here and take that. So X belongs to such that X belongs to a intersection. Intersection can be written as that X does not belong to A intersection B. Does not belong should be written like that, right? So that takes care of this particular area zone, and we need to talk about that zone, right? So or it's a union X belongs to B intersection. I'm going to remove this guy, it's going to interfere with us, and X does not belong to A intersection B. So right, so we have written the definition of set difference of two sets A and B in this form, right? Now we need to go and let's rewrite this, right? How do we rewrite this? I'm going to see if there's a way I can do that. Yeah. So X, so I'm going to rewrite this particular stuff. Okay. This stuff. So how do I do it? So X belongs to A intersection X belongs to A intersection B complement, right? That's a complement. Or X belongs to B intersection X belongs to A intersection B complement. So that we rewrote this previous set identity builder into this, right? So we need to close these parentheses, so we have to be very careful with that, right? So now if you expand this using the De Morgan's law, we just showed you the De Morgan's law states that if you see the De Morgan's law, we have two laws, right? So here A intersection B complement, A intersection B complement can be written as A complement union B complement, right? So we can rewrite that. X belongs to A intersection X belongs to A complement union B complement, or now we need to rewrite, we're rewriting this guy, right? X belongs to B intersection, this is again De Morgan's law, right? X belongs to A complement union B complement, and close this and close this. So we have basically applied De Morgan's law. Now we need to apply uh, the uh, the distributive law. So what is the distributive law states? You see here, we have to take, we have to take this particular stuff and apply distributive law. See here, intersection we have a union here, so we have to take that distributive law, right? Intersection followed by, see here. So we need to apply, expand this into this, right? So we'll go ahead and do it. So how do we apply that? How do we apply that? So we have, I actually write should be like the X such that it's not. Anyway, so now I have to expand. So how do I expand this? This expansion is X belongs to A intersection X belongs to A complement. Now the union, I have to worry about this union, right? Union, I need the black color. Union, let's keep it that. X belongs to A intersection X belongs to B complement. So we basically expanded this term into this term using distributive law. Now we need to expand this guy. So let's go ahead and do it. Or remember this and this you can mix, don't mix, don't, they go together always, right? Eventually they will merge, but now we need to expand this X using distributive law. Intersection X belongs to A complement, right? That's union X complement B intersection X complement. Okay, so we applied distributive law to that. So now if you see these two terms is kind of weird here. X belongs to A intersection X belongs to complement, that will be empty, right? This is empty set. Similarly, this is empty set. So we can ignore pretty much, right? So if you want to know why, here. Is always empty, right? So that's what we have here. So that is empty. So that's left with us is the remaining two terms, this term and this term, right? So let's take this particular guy. So what does this mean? So let's just summarize that. That way is easy. X such that we're just going to copy that term here. or this term we're going to not going to do it because empty. We're going to take the remaining set. All right, then what you got here? A x belongs to A and x belongs to BC. What does it mean? This is a, can we write as a set difference law? So let's go to set difference law. What does it do? A set difference law. Here it is. So x belongs to A intersection x belongs to B complement. You see this guy? You see this guy? You have to apply there. So apply, when you apply, what happens? It means x belongs to A minus B, or, and the same thing here, right? Same, x belongs to B minus A. So this is, what is the definition of this guy? It's a union, right? X such that x belongs to A minus B union, sorry, B minus A, and that's what we got here, right? We proved that, quite easily done. So you have to know all the rules that laws that we used, right, to go from the basic definition. We took the basic definition of a symmetric difference of A and B, and then we expanded to prove that if an element X, it belongs to set difference of A and B, it also belongs to A minus B union B minus A. So that is a one proof we have. All right, and slowly we used De Morgan's law, we used distributive law, and we used other set difference laws. So all that we have used to derive the next step. And if you have to state, every time you do from one step to another step, you have to specify what kind of law did you use to arrive at that equation. And so this is one simple video on the set difference law. Okay, thank you.